Hello, welcome back everybody. Apologies for the short break, but in the interest of time, we're going to press on with the next session. So I'm really pleased to be able to introduce you all to Professor Gerhard Diller, who I'm sure needs no introduction to many of you. So Gerhard is a professor and consultant in cardiology and ACHD at the University Hospital in Münster. Over the years, his interests have included pulmonary hypertension and ventricular function. And I'm sure many of you are familiar with his numerous publications. More recently, though, Gerhard's become had an interest in health economics, and subsequently this has led on to an interest in artificial intelligence and machine learning. He's applied this to ACHD. So welcome, Gerhard. Really looking forward to hearing your talk and seeing what you can tell us about what we could be doing, should be doing, might be doing in the future with regards to AI and machine learning. Welcome.
Okay. Thank you, Natali, for this kind introduction, and thank you to all the organizers and Michael, and, particularly for inviting me to give this presentation. So it's a particular honor and pleasure for me to speak about this topic. So I have no conflict of interest to declare related to this topic. So what is the scope of machine learning or artificial intelligence in adults with congenital heart disease? Well, as you probably know, we have around 4 million patients with congenital heart disease in Europe, and congenital heart disease is a lifelong chronic condition that requires repeated investigations and follow-up, and this is a long process that is time-consuming and very expensive. And so the traditional models of care that we are used to tend to be quite inefficient and fragmented, and I think there is a need for newer, smarter, patient-centered approaches globally. So natural history and prognosis studies have been at the heart of adult congenital heart disease research for decades, but again, in this area, we need maybe better and smarter tools to help us with our daily work. And there are some disruptive impact aspects of artificial intelligence that have been postulated, mostly related to the multimodality input and the scalability, and I will speak about this during the presentation as well. And again, as you know, there is a global interest in machine learning, artificial intelligence. There's huge funding of projects related to artificial intelligence in general, but specifically also in healthcare, and that is a global phenomenon. And in general, we've witnessed a paradigm shift from rule-based programming that we have seen over decades in computer science to neural networks. And this is mainly due to the success of artificial intelligence and machine learning that we're all familiar with from our daily lives. Current technology of artificial intelligence achieves near human-level image classification, near human-level speech recognition, machine translations. We know the digital assistants that we have, Alexa and Siri in our mobile phones, for example, and there is ability to answer natural language questions. And as you can see from the pictures at the bottom of this slides, there are some very impressive results that can be generated with neural networks and deep learning networks. One is this generative adversarial network on the left that takes a movie of a horse and transforms it live into a zebra, and the example on the right is sort of artificially created human faces. So those are not pictures of humans; those are artificially created pictures of human faces. So there are two approaches that we can take when we are faced with a problem. One is to have a very algorithmic approach using logical reasoning and the experience that we have and what we've learned about the pathophysiology and anatomy of a problem, and then sort of deduct from this a solution for the problem. This is very much a preferred approach as long as we fully understand the problem, and the problem can be modeled in terms of such an algorithmic approach. On the other hand, we are also very familiar with examples from our daily life of actions and things which cannot be put into such an algorithmic approach. One good example, I guess, is bicycle riding. You cannot logically explain to somebody how to ride their bike. They have to try it themselves. They have to try. They have to fail. They try again, and at some point they will know how to ride their bike. And then once they know how to ride their bike, the problem is, of course, that it's very difficult for them to explain to another person how they did it. So this is what artificial intelligence basically does, and machine learning networks. They are mimicking this type of try and fail approach. In general, just to give you a very high-level overview of a machine learning and deep learning networks, they are modeled on the example of the human brain, so a bit like a neuron with a number of inputs and a number of outputs that are interconnected nodes and layers. And so you put in a multidimensional input, for example, a picture, and you get a lower dimensional output out of the network, for example, a classification saying that this is a picture of a dog or a horse or something else. I think the more important thing to understand about neural network is that they are sort of high-dimensional statistical models, more or less. So they are mathematical models that map a high-dimensional input to a lower-dimensional input using a complex nonlinear function. And the way they do it is very similar to the bicycle example that I show you. So you take a pristine neural network, you input data into it, it will run through the network, it will come out with some random prediction, because the network knows nothing about the problem at hand. And then it will optimize the weight slightly, and then it will try again and again, and it will fail again. And by trying again and failing again, it will learn and adapt these weights. And in the end, hopefully, the neural network will be able to deliver the results that we expected to do so. So when you listen to talks about machine learning, there is a lot of talk about what could be done and how it will transform everything. But I want to take a slightly different approach in this talk. I just want to give you some examples about how neural networks and deep learning might be applicable to congenital heart disease based on some of our publications that we published jointly with the Brompton and the German Network for Congenital Heart Disease. Looking at natural language processing, looking at image classification, looking at the big problem of image segmentation, that is to sort of delineate the endocardial border of the cardiac chambers to enable measurement of ventricular size and function, for example, and some aspects of image augmentation as well. So hopefully by looking at this example, you will get an idea of what is currently possible, and then we can speak about what is theoretically possible in the future and where the journey will lead us to. So this is an example of image classification. This is not from our work. This is also not from congenital heart disease. This is a large study that was published in Circulation in 2018. And basically what the authors have done, they've taken echo studies and used a classification model to enable them to predict which echocardiographic view we are looking at, so if it's a long axis view or a full chamber view, and also to do some disease detection. And this worked reasonably well for them in this feasibility study that has been published in Circulation. And this technology, I think, will come our ways one way or another, because the big vendors of echocardiographic machines will probably within the next next future, they will implement these technologies into the echo machine. So at least this image view classification will be available in the newer generation echo machines. So this is an example from our approach to classification using machine learning in congenital heart disease. And this again is a feasibility study that we published in 2019 jointly with the with Münster University and the Brompton Hospital. And basically the question that we had in this study is, can you train a machine learning system to classify echocardiographic images of hearts into normal hearts, into TGA hearts after arterial switch and CCTGA hearts using a 4-chamber view and short axis views, and how well might this be possible with a machine learning approach. So basically what we had echo studies from normal hearts, 67 patients, atrial switch, TGA, 92 patients, and CCTGA, 40 patients, and we had this echocardiographic 4-chamber and short axis views. And as you can imagine, there are many more echo frames than you have echo studies. So we're talking about 10 to 30,000 of echo frames that we used for training in this example. And then we used such a deep learning network that is depicted here. It's a so-called convolutional network that uses an image and provides you with a classification response. So in this case, it looks at images, echocardiographic images of the heart, and gives you a prediction whether this is a heart from a CCTGA, TGA, or a normal heart. And when we did this, we actually had very good results in the validation sample. So one thing that I might have to say is that you have to train this model on one data set and then validate it on a different data set from different patients to really understand how good the model performs in an external data set. And when we did this on the external data set, 95 to 99% of frames were accurately classified into the correct diagnosis. And when we combined the frames from one echo study into a stack and presented the model with that, almost all the patients were correctly classified. And again, as you can see from this picture up here, the model even sort of understood which was this the systemic ventricle in this patient. So it activated predominantly on the systemic ventricle in this sample. So this is, I think, a proof of concept that such classification systems can be built and can have relatively good results in correctly classifying the diagnosis based on routine echocardiographic imaging. Now, not all echocardiographic or imaging studies that we obtain from our patients have the best quality. And another potential approach to use machine learning in this setting is to use a deep learning network to augment the quality of this investigation. So this is a model that we built based on a so-called autoencoder that takes a quite a noisy picture of a heart and some denoising, so improves the image quality in this upper panel example. And in the lower panel example, as you can see, it sort of removes an acoustic artifact, this cancellation sector artifact from echocardiographic image. And I think the main application of such models is to improve the image quality for downstream classification and segmentation networks. The other thing that where machine learning algorithms and deep learning may be quite helpful in our practice is we're faced with a lot of data, a lot of written reports from our patients spanning, multiple decades of care in our patients, and it would be nice to have some tool that looks at this unstructured medical reports and extracts some useful information from that, and maybe even provide maybe less experienced colleagues with some hints what the diagnosis might be, what the complexity of disease might be, how these patients might be treated at specialist centers, and maybe what the prognosis of the patients is based on this raw text data. And we did this based on a data set from Royal Brompton Hospital, including more than 10,000 patients. As you can see here, 10,019 adult patients with congenital heart disease, 44,000 letters. So, of course, as you would expect, many patients had multiple clinical visits during this study period, during this retrospective study period, of course. And we extracted raw text data from these medical reports. We also had access to ECG parameters, cardiopulmonary exercise testing, and some laboratory markers in this data. And then we, based on this information, we then built deep learning networks to categorize diagnostic group, disease complexity, NIH class, and to predict survival and medical therapy in this population. And this is just a very high-level overview over the network. As you can see, it is fed with this raw data from the medical records. The data from medical records is not altered in any way, except that we remove capital letters, so it's all lower letters. And then the raw data is fed into the model we have the diagnostic block, we have the apart from the letter and the convolutional networks that are expected to come out with some useful information based on this raw data. And what we found is that it's quite possible with a good accuracy to predict the diagnostic group of these patients. As you can see in this example, there's raw text that goes into the diagnosis fields, and then the computer comes out with the diagnosis, the complexity of disease. In the NIH class, based on the first paragraph of the letter, was relatively well detected. And then based on all this information and including some numerical data, the prognosis of the patients was predicted. I think this is an exciting, again, proof of concept study based on a single center from the Royal Brompton, and we're awaiting external validation of this data set, but I think it shows how much potential this type of analysis may have to assist care for a patient with congenital heart disease, maybe the community and in less experienced centers. Coming to the fourth area where machine learning and deep learning might be applicable is segmentation. Now, segmentation, I think, is one of the major things that we encounter when we do clinical imaging. Of course, everything that we do in the echo lab or in the MRI, when we want to sort of quantify ventricular dimensions or ventricular function, we have to delineate the endocardial border of the respective cardiac chambers, and this is normally a very labor-intensive, manual, time-consuming process, which has to be done on each frame. And there is a promise that machine learning might be able to assist us with that and increase efficiency, and also give us access to much more data than we used to have before, because we then can just harvest the entire data that is present in this data set, as opposed to just focusing on some measurements that we might just be able to do within limited time we have to report this investigation. And this is a study that we did together with the German National Registry for Congenital Heart Disease on MRIs from patients with tetralogy of Fallot. So what we did in this study, we trained deep learning networks to recognize the right ventricle, left ventricle, and the right atrium in long axis and short axis used for cardiac MRIs. And for this, we'll use the local training set from the Münster University Hospital. So this was data that was completely external to the data set that we wanted to study and to analyze. And then we built a deep learning network that takes this raw image data and then produces these masks. As you can see in this example, we presented with this grayscale image, and then the red border is produced automatically by the network. So it delineates the right ventricle, left ventricle, and the right atrium. And this is on a frame-by-frame basis, but then can be combined into a sort of a stack of the entire investigation. And based on that, we wanted to quantify ventricular dimension and function and understand whether this information could be used to build a fully automatic prognostication tool. So just looking at the MRI, can this model predict prognosis of patients? So what we used for that, as I explained to you, we trained a model on a local data set, which was external to the data set that we then validated the model on, and the validation data set was a data set from the National Registry for Congenital Heart Disease in Germany. They had cardiac MRIs from 14 German centers that were collected before 2010, and that included roughly 400 patients with tetralogy of Fallot. All these patients had MRIs. According to an agreed protocol, the data went to a core lab and there was quality assurance there, and this data was archived and was available for our study. So we could apply our trained models to measure area and the polygon length. And if you think about it, if you measure area, it gives you something like fraction area change, so a measure of ventricular function. If you look at the border length, at the polygon length, it gives you a global strain measure. And we applied these measures to correlate with prognosis in these patients and investigate whether one could build a fully automated prognostic model. This is just to show you how this model looks. You can see on the left hand corner, upper corner, the raw MRI stack that came from the core lab, and then we had the program that actually rotates the image, crops out the heart, and then enables segmentation in a fully automated way. And these are just examples of the quality of the segmentation that we obtained, and the measurements of areas and curve lengths of strain over the cardiac cycle. So this technology worked pretty well in our hands for this data set. And then we went on to build a prognostic model based on this data. As you can see here, a number of parameters were predictive of outcome. We included 372 patients from this registry. The median follow-up was 10 years. There were not too many events in this data set because the median age of these patients was less than 20 years in this data set. But as you can see from this analysis, a number of parameters were predictive to outcome. This includes conventional MRI parameters, as you would expect, ejection fraction, volumes, but also quite a large number of deep learning-based, automatically derived measures, mainly area-based and strain-based. And when we focused on right atrial area and right ventricular strain, you can actually see that if you quantify patients by this fully automated measures, you can come up with a decent prognostication in this data set. So again, this is a proof of concept feasibility study, but just showing the potential of the technology of using the data that we have and enabling, as I said, a more or less fully automatic prognostication in this data set. In our study, we used machine learning really to delineate the ventricles and come up with the conventional measures of area and function and strain that we normally measure to relate to prognosis. You can actually take this whole technology a step further. This is data from Imperial College in London, published in 2019. And what they did in pulmonary hypertension is they actually took MRI images and fed them into a deep learning network that was not provided with such measures. It was sort of left alone to come up with an algorithm that predicts prognosis. So you basically, in this quite complex algorithm and this complex slide, what you basically do is you provide the raw data into the model and you expect it to reconstruct the data, but you also expect it to come up with a survival information from this data. As I said, without sort of giving the model any information on measuring ejection fraction or strain or anything like that. And even that was possible. So you have a completely black box system that really looks at the data and comes up with prognostication model. So whether this is the future, I don't know, but this is certainly on the horizon as a way to build prognostication models based on imaging data. So what is the future? Why are we doing this? Well, I think this fits very well with what Harris presented yesterday when he was talking about technology. The idea is, of course, to come up with personalized medicine, to integrate various modalities into one deep learning network, starting with unstructured medical reports with imaging data, but also mobile data, real-time data from ECG, saturation measurements, whatever you can think of, and then come up with a prognostic model that is above all it's scalable. So it doesn't matter whether you include 1,000 patients or 10,000 or 100,000 patients. These models can deal with a lot of data. And in the end, of course, the idea is, as coined by Siemens, for example, is to create something like a digital twin of the patients, a model of the patients where we can understand what is most likely to happen to this patient. So just to conclude, I just wanted to give you an overview of where I think artificial intelligence is currently standing in adults with congenital heart disease. I think artificial intelligence is here to stay. It's definitely a major breakthrough in cardiology, including adults with congenital heart disease. There are many applications that one can think of for machine learning or artificial intelligence in this setting. What we really need, I think, is clinically motivated and tailored applications that fit the patient's need. One thing is, I think, quite clear: artificial intelligence is more efficient than human assessment of, for example, ventricular function, because it's just much faster. There are issues, however, that we have to solve. It's not specific to congenital heart disease, of course. The data sources have to be transparent. There needs to be accountability. So just, of course, the obvious question is, if something goes wrong, who is to blame? Is it the system? Who will take responsibility for if treatment decisions are not the way that we expect them? And the other thing that I want to conclude with is, I think it is pretty clear that these applications will be developed by various companies. There's a lot of commercial interest in developing machine learning applications for cardiac patients. But what our role needs to be as congenital cardiologists is to focus on our patients, to develop focused systems for our patients, because I think if you leave it entirely to the large companies to come up with the solutions, they will probably fail our patients. They will be trained on acquired heart disease, on different anatomies, and they will not be able to deliver the results that we expect for our patients. So I think we have to invest ourselves into developing AI technology for adults with congenital heart disease. I just want to finish with this pictures. Unfortunately, it's a virtual conference, so you can't go to the National Gallery to look at this picture of William Turnell, the fighting Temeraire, that was, by the way, featured in Skyfall in James Bond, and was voted the greatest British painting in 2005. But what it really shows, I think, is this proud old battleship, the Temeraire, which was one of Nelson's flagship ships in the great Battle of Trafalgar, being pulled to be broken down by this steamship. So I think you cannot stop innovation. You just have to build on innovation and develop applications that fit our needs. Thank you very much.
Sorry, forgot to unmute myself. Thank you for that great overview and introduction to actually the application of AI already in ACHD and potential suggestions of where we might go with this. So I just start with a question, but the audience, please feel free to add any questions that you might have to the chat. You talk about us not waiting for other companies or the bigger cardiology population perhaps to take this work forward, but to take the work forward ourselves with our ACHD patients. And to do that, presumably the bigger the data volume, the better. How do you count or take into account security when thinking about downloading different pools of data across multiple centers, if, for example, we were to take forward a multi-center study?
Yes, I think this is an important question, of course. There are technical solutions to this, to train models on different servers at the same time. The other obvious solution is to anonymize the data, especially for imaging data. This should be possible if you remove any sort of patient information from the image. And the other thing that you can actually do with these models, you can if you have one data set, you can train a model, but it doesn't stop there. You can take the trained model and retrain it on a different data set at a different center. So you can run multiple cycles of training, and every time it sort of improves the training that you give to the model. So you could actually visit a project that trains on echo data at the Brompton, and then you sort of take the trained model to a computer at St. Thomas's and retrain it there, and take it to, I don't know, to some other place, and then retrain it there. So I think this is possible. But of course, there are issues with data security, like everything that has to do with big data. I think this is sort of something to keep in mind. I fully agree with you.
Will you be around? I assume people can post you questions on the contact you directly on the chat during the lunch break.
Sure, of course.
Yeah. Okay. So in the interest of time, we're going to have a lunch break shortly. Can I just ask you though, Gerhard, before lunch, how do we sell this to patients, do you think? Have you had any input as yet or discussions with patient groups about what they think about their data being used in this way?
Well, I think the discussions that we had with patients were actually quite positive. I think patients, at least from my experiences, are very keen to move research forward into congenital heart disease, and so they are quite supported. Some of the research that I presented is actually, in a way, sort of financially supported by patient organizations and different funders that are very close to patient organizations. So there is a lot of interest from patients, and I think it's the same issues that apply to any research study. Of course, confidentiality issues are a point, but patients really are interested in this, and they see it on the media, and they see that this is coming. So they're very keen to also benefit within congenital heart disease from this new technology. At least that's my experience that I have.
Yeah, absolutely. I mean, I think with as previous speakers already alluded to, the move towards being able to prognosticate better, to be able to give patients better quality of life in reducing the number of visits that they need to hospitals, but at the same time being able to reassure them that actually those extra visits aren't needed, they're okay, it would be really, really important. So thank you very much, Gerhard. I forgot to mention at the end that you are also, as well as working in Munster and the Brompton, a visiting professor at King's. So from that point of view, I look forward to working with you in the future months with regard to this.